Okay. Hello, everyone. Do you have any questions from the last time? Oh, yeah. Not, then let us continue. So actually, I decided to change conventions a little bit because these minus signs are really annoying. Today we'll continue studying this Sturm-Liouville theory, but we'll choose the operator in this form. 1 over w of x minus d in dx p of x d in dx plus q of x. And now the condition will be that q of x is bounded from below. And there is also a scalar product defined like this. From A to B. So why it is nice? Because if I now compute the so how to call it, such kind of matrix element between F and F. If we act on F and multiply it again by F, it is like computing diagonal elements of L, then this integral can be written as follows. So it is, let us simply write what we have. Integral over dx. So now this can be integrated by parts. It is minus f bar f prime p of x from A to B, and this will be the integral dx p of x f bar prime, well, f prime absolute value squared plus absolute value of f squared and q of x. So, for example, if q of x is positive, and it can be made positive simply by shifting this operator by some constant, then this integral is always positive. So this can be made positive. And concerning this term, we have this boundary conditions that f prime is expressible through f on the boundaries. So this can be written as minus plus absolute value of f squared f of b squared, something like beta over beta tilde over beta minus absolute value of f of a squared alpha tilde over alpha. So this alpha and beta are coefficients in the boundary conditions. So namely, boundary conditions are this alpha of a prime of alpha tilde of a p of a f prime of a plus oh sorry alpha plus alpha f of a equals to 0, and the same on the other boundary. So, and I'm using this relation to rewrite this. It can also be written in the opposite way through f prime. So the point is that if there are some conditions on this constants, for example, these constants have the same sign, these constants have the opposite sign, then the term can also be made positive. And the meaning of this is that such boundary conditions correspond to some strings attached to the ends of string, and they have either a positive or a negative elasticity coefficient. Like their energy can be either negative or positive. And a good physical problem is when the energy is positive. So. Yes. Yes. And, uh, the spectral problem we are solving is the following. So L Fn equals to lambda n Fn without minus sign. Oh, it is a change of sign in Q in a sense. Originally it was bounded from above and now it is bounded from below. So if we write it this way, then it is a quantum mechanical kinetic energy operator. It is minus d in dx squared, and this is a quantum mechanical potential energy operator. And before that, they were with minus signs. So I think this is a better notation. Mm. Yeah. So. This way, so if this Q is bounded from below, then we can simply shift it by its minimal value and make all the terms simply positive. So it does not affect anything. We simply shift operator by constant and all its eigenvalues also by constant. So now we know that this is this object is positive. Um, uh, so it's definitely greater than 0. And we can consider the following functional. Let's call it E, like energy, E of phi or psi of psi equals to psi L psi over psi comma psi. So it is also positive. So mm, mm, so bounded from below, and we are asking the following question: what is the minimum of this functional? So it's a kind of a rational problem. We need to substitute e of psi plus dot of psi and ask this first variation to vanish. So let us say that we substitute here. So we study e of psi plus epsilon dot of psi. So this equals to so there will be coefficient 2. Well, let us simply write all the terms. It will be e of psi, original expression, plus epsilon psi l dot of psi, for psi plus epsilon dot of psi l psi over psi minus 2 epsilon psi l psi over psi squared psi dot of psi, right? Plus O of epsilon squared. So we write it as E of psi plus epsilon delta E of psi plus O of epsilon squared. So this delta E of psi is simply the coefficient in front of epsilon. And, so let us now study this delta E of psi. So we see that these two terms are equal because L is symmetric, self-invariant, and so on. So we can simply move it to this term in the scalar product. So delta E of psi will be 2 psi squared in the denominator, and here maybe it's not the best way to write it, but anyway, so here we have psi scalar product with L, delta psi scalar product with L psi times psi minus delta psi with psi psi scalar product with L psi. And we would like to write it as a scalar product of delta psi with some operator. So it can be done like this. It is let me think. Oh, let us simplify what we have. So delta psi, a scalar product with 1 over psi psi, L psi in one term. In the other term, it is psi times this ratio. Maybe it's better to move 1 over psi psi the overall factor. It will be 2 over psi psi delta psi L psi minus psi L psi or psi psi psi. And if it is a minimum, we want it to be 0 for any delta psi. So since we are studying this operator on the space of all twice integrable or twice differentiable functions, and then we can construct even an infinitely smooth function that is non-vanishing some small interval, and this way we can check that this expression should vanish for any x. So we simply have an equation that L psi minus psi L psi over psi equals to 0. So in other words, L psi equals to some number times psi. Psi is the eigenvector. A function that satisfy these boundary conditions and are twice differentiable should be enough.
They shouldn't be like some kind of variation of psi, like some. Okay, so they are just any two times differentiable function.
Yes. But we can ask it even for infinitely smooth functions with complex support. It is still enough to have this equation. We actually use such functions to say that it is 0. So if scalar product of some function or with some other function, so if a scalar product of something with any function is 0, then we know that these functions are at least continuous, then it should be 0. Because we can only construct some pathological examples with a function that is equal to 1 at some points and 0 everywhere else. So find that this this that extremes of this function also correspond to eigenvalues of L, and psi's correspond to eigenvectors. Yeah, and we also we can also say that all this is bounded from below. So there will be some minimal eigenvalue. Well, I don't know, probably should be some proof that there are no concentrations of small eigenvalues. But it actually follows from the properties of this equation, and we will study this later. In a sense, we will study the eigenfunctions of such operators later. But now we can say there is some lambda 1, so there is so the actual minimum of this function is lambda 1. Not just extremum, but minimum. Let us actually call this E0. Let us call this functional. No, let it be E. So it is a minimum of E on the whole space. Let's call the space H. And but now let us remember that this that if you take and there is psi 1, which is well, psi equals f1 is the point on which this minimum is achieved. How good. In a sense, L f1 equals to lambda 1 f1. So once we know this, we can go further and say that okay, we found this minimum on the whole space, and now let us consider orthogonal complement of the space, orthogonal complement of f1, and define lambda 2. So f1 is invariant on the direction of L. So now let us define lambda 2 as minimum of this E on orthogonal complement. We can do this, right? And so on. So lambda 3 is minimum on orthogonal complement of f1 and f2. Lambda 4 the same on f1, f2, 2 f3
we have a countable number of eigenvalues.
It's
If they are bounded from below, we shouldn't conclude, we couldn't conclude that they are
we need to study the properties of this operators, so we will do it later. But you saw in the examples that this first, that all eigenvalues are separated. There are no concentrations. It is just some discrete set, which and lambda n behave like n squared. So. Yes.
yes, but in general,
No, we'll study it later. And now we suppose that everything works as in these examples, and prove that in this case we have this basis in our Hilbert space given by the eigenfunctions of L. Yes, so we define this eigenvalues as minimum, as minimal this functional on the orthogonal complement, and so we see that if we take some vector in the orthogonal, now let us study some function which we want to expand in this basis. So we want to expand some function phi. And let us study projection operator that projects on the orthogonal complement to first n eigenvectors. So define Pn as identity operator minus a sum of 1 over let us define Pn phi as 1 minus sum from n equals to 1 to n like this. So we can also be written as 1 minus 1 minus Pn prime on phi. So this is on the projector onto first n eigenvectors, and this is a projector on the orthogonal complement. And there are properties like Pn squared equals to Pn, and Pn prime squared equals to Pn prime, and Pn prime times Pn equals Pn prime equals to 0. So they are orthogonal projectors. So is it more or less obvious or not? We can think about them as uh, as about such matrices. So Pn prime is this identity matrix 0. This is Pn prime, and Pn is in this matrix, which is infinite, and here there are zeros. Is it okay? And this projectors commute with L. So, Pn with L equals to L in Pn. So it can be thought as that if we choose such a basis, then L is written simply as a diagonal matrix of 1, lambda 1, and lambda 2, and so on. So so now we can compute a scalar product of Pn phi with L Pn phi. So we know that this vector is orthogonal to all fn's until big N. So, and we know that minimum of this functional on of the ratio of this and norm of this vector, this functional is greater or equal than lambda n. So it is greater or equal than lambda n plus 1. Pn phi, Pn phi, right? Because Pn Pn phi is in the orthogonal complement to f1 fn. And the eigenvalue of L so a minimum of this ratio on such a space is lambda n plus 1 by this construction. So we simply consider a vector and this orthogonal complement. Hmm? Hmm? Yes. So this ratio is greater or equal than lambda n plus 1.
No, già, sì, sì, ho capito.
Is it fine? Okay.
I was wondering because the structure of the okay, I was thinking that the structure of the minima are of the kind psi at psi or psi. So is that okay? And then plus one the minima, and so it's less or equal.
Oh, on this ratio, right?
Esatto, esatto. Se tu dividi,
No. What is the question?
no. Okay, no, never mind.
Simply saying that we substitute here p and phi instead of psi, and we know since a minimum of this function on the space where this vector belongs is lambda n plus 1, so if you compute on this vector, it's definitely greater than lambda n plus 1. So so we have this restriction. And we can write that this scalar product Pn phi is less or equal than 1 over lambda n plus 1 of this scalar product. And actually, let us simply write this, and then we'll simplify it a little bit. So, so we can write it as, no, let us first write it as this. And then rewrite as 1 lambda n plus 1 phi minus Pn prime phi L phi minus L Pn prime phi, which is one term will be phi L phi minus what? Minus P n prime phi L phi minus phi L P n prime phi plus we can also check that this operator is is a Hermitian in this projection operator. And so we can, so all these three terms are equal. So it commutes with L, it is a Hermitian. Oh, maybe I can add in these properties here. Then f of g equals to f Pn with g, and the same for p prime. So using this, using commutativity with L, using this property that p square equals to p, we can write this simply as 1 over lambda n plus 1 phi L phi minus p n prime phi L p n prime phi. And since we have chosen else such that it is positive, we can say that all this is less or equal, or simply less than, or less or equal than 1 over lambda n plus 1 phi L phi. Right? So and it goes to 0.
So you also using the fact that no, why okay, the Pn is a Hessian, but why this implies that the second term and the first term vanishes.
No, they don't vanish. They are all equal. And this equals to this.
Yeah, I mean vanish together.
Oh, we can simply introduce, so we can write here Pn squared, because Pn squared equals to Pn, and then move one of these Pns to the first place. And we can do the same, and then move one of them here. These terms become the same. Mm.
So there is the plus there.
No, it's minus plus. Hmm? Um, There are two terms with minus and one term with plus.
Okay. Okay.
Mhm. So if you write it in terms of these matrices, then it is simply a statement that if you compute a scalar product of vectors projected with this projector, it equals to scalar products of vector to scalar product of vectors without any projectors minus scalar product with this projector. It's simply this. Maybe it can be some simpler way to prove this, but uh, so if it doesn't look convincing, you can simply substitute this definition and compute what it gives. It will be a little bit longer, but mm, more explicit.
But why you know that the second term in the last like p and prime phi scalar product and p and prime phi is positive?
Because I started from this, I said that since a Q is bounded from below, we can, without loss of generality, we can simply shift it by some constant to make positive, and then all such expressions become positive. Right. Maybe it's not necessary in a sense. Oh, actually, we want all the eigenvalues to be bounded from below, so we can perform such shift. Maybe the only question is about this boundary conditions, like what happens if we choose wrong signs of this constants. But I'm actually not sure that it is an innocent procedure, in a sense that if we add some string with negative elasticity coefficient, it is something unphysical and probably can lead to some problems. So I'm not sure, but probably is better not to do this. So this boundary terms should be positive. But in most cases, it will be just zero because we impose boundary conditions with either f prime or f equal to zero at the boundary. Okay. So and now let us study the properties of this Sturm-Liouville eigenfunctions. Yes, here at the end of proof, we see that if subtract orthogonal projection of our phi onto first n vectors, this goes to zero. So if we send n to infinity, we will have that kind of L2 convergence of this analog of the Fourier series to our original function. So.
We actually need also need a stick to prove that lambda n goes to infinity.
Yes, and we are going to do this now. Yeah. So, properties of there is a so-called Sturm comparison theorem, uh, which tells us what happens when we change the eigenvalue in this operator. So, Actually, let me think. I also want to make the following remark about different forms of this Sturm-Liouville operator. Uh, So we have this original operator, and its remarkable property is that it is orthogonal with weight W, which is written explicitly. But we can also, this operator contains uh, some first derivative. Uh, so I want to say that there is a way to get rid of this first derivative. Mm. So it's a different form of f. So we want to say that we want to introduce some new. We want to say that f is some function. Let us call it a times e to the a, maybe even e to the a is fine, times f tilde. And let us substitute it into the Sturm-Liouville equation. So minus d in dx p of x d in dx e to a f tilde plus 2 e to the a f tilde equals to lambda e to the a f tilde. So now we can multiply everything by e to minus a and compute commutator with these derivatives. Well, maybe better, simply better to differentiate all this simply. Yes. Well, I'm not writing this x dependence everywhere, but it is assumed. Otherwise, it doesn't make sense. So it is minus d in dx p of x e to e to minus a. So we can do this. Then we also differentiate all this. So the other term when we differentiate p, it will be minus p prime f tilde prime f tilde prime plus a prime f tilde. Then there is a term when we differentiate this exponential. It will be minus PA prime F tilde prime, so another term of this kind. Then there is a term when we differentiate this F tilde, will be minus P F tilde with two primes. Sorry, here is W. It's a W. So then there is a term when we differentiate this A prime. No, minus sign primes F tilde, and then e to the A F tilde plus, for the last term when we differentiate F tilde. Plus QF equals to lambda W F. So there are all these terms, and let us rewrite it somewhere. Maybe here.
A second tilde minus r prime to the second power tilde shouldn't be p times that stuff.
Yes, thanks. It's everywhere. No, probably it's fine, right? Seems to be fine. So now let us collect everything. So we have first we have F tilde with two primes, just one term of this kind. Pf tilde with two primes. Then we have F with minus sign, F tilde prime, and let us collect all the terms which are there. So there is a P prime coming from here. And then there is a PA prime. And then there is so prime. Another prime is here with the same coefficient plus PA prime. And that's all, right? Now let us collect all other coefficients. Minus F, maybe plus F, we have this minus p prime a prime. Then minus p a with 2 primes minus p a prime squared. So is it? Oh, yes, I think yes, plus q. And we can actually, oh, it equals to lambda w, lambda w f tilde. So like this, and we want to get rid of this term. We want this function to satisfy an equation without first derivative in f, because then it is simple to study such equations. So we simply put p a equals to 1 over square root of p, because a condition that this no, sorry, we want to find a in terms of p. So this gives us that a prime is d log of a in dx equals to minus oh wait, what am I writing? A prime equals to a minus 1/2 d log p in dx. So we can say that a is minus 1/2 log of p. So our f tilde, or f in terms of f tilde, is 1 over square root of p f tilde. So if you do this, then this term disappears. So, and we have an equation of this form: f2 primes minus f2 primes f tilde 2 primes plus some q tilde. It will be some different potential. Q tilde f tilde equals to lambda w tilde f tilde. So we can simply divide by p and get something on the right hand side. So if you want to study something, we can in principle stick to this equation, and everything else will be similar. So I will use it sometimes when it will become too hard. So, but a bit lengthy remark. Now, you can in principle study the general case without such a transformation. So we can, and also another remark is that such transformation does not affect zeros of f. So if you study zeros of f tilde, they will be the same as zeros of f. So let us consider the following situation. We have two functions that satisfy different equations. So we can even consider a different different functions here. But for now, let us or maybe let us study the general case from the beginning. So let us say that there is one function that satisfies such equation. F prime of x no, wait. We can always simplify the problem, but let us start from the general case. So we have one function that satisfies this equation. Lambda 1 W1. And we have another function that satisfies this equation with a right-hand side bigger than in this equation. For example, it can happen because we have chosen a bigger value of lambda. Oh, sorry, I forgot this term. And it is g. And this lambda 2w2 greater than lambda 1 w1. So this comparison theorem says that if we take two zeros of w2, then this interval will of g, then this interval will contain at least one zero of f. So let us call x1 and x2 zeros of g. Then this interval, open interval, so in particular, it happens if we simply increase increase lambda. But it can also happen if we consider some different equation, but on the same p. So let's prove this. So illustration for this is the following. So suppose that we are studying two eigenfunctions of a simply derivative operator, and it will be our basic example. So there is some there is this real line, and we have some sign that oscillates on this way. And then we increase lambda a little bit. So the new sine function will oscillate faster. So the first zero will appear earlier, then the second zero will be somewhere here, then there will be this zero. Something like this. And sometimes we can even have two zeros in some intervals, I think. But idea is that if zeros of one functions are more dense, oh, maybe it's better to say so that that if we increase lambda or the right hand side in general, then zeros of this function become more dense, and they become dense in this way, that zeros of function with a higher eigenvalue are placed between zeros of function with lower eigenvalue. At least one. So let us prove this. And to do this, we need to consider the Vronsky of this functions, which can be obtained in the following way. We take this first equation and multiply by a second function, or vice versa. It's the same. So we simply say that and we integrate this thing between zeros of g. So integral from x.
Sorry. I mean, x1, x2 are two consecutive zero.
Yes. Yes. From x1 to x2. So we are taking this equations. Basically, no. What am I saying? No, we should multiply one equation by f, another equation by g, and subtract like this. So we want to study the integral from x1 to x2 dx of f times g times lambda 2 and w2 minus lambda 1 w1. So it's one side of equality. We simply want to consider on this function. And in the other side, we substitute the left-hand side of these equations. From integral from x1 to x2. So in this case, we substitute this operator acting on g. It will be f times minus p g prime plus q g. And here it is g times minus p prime plus qf dx. I simply substitute equation they satisfy. Now we integrate this by parts, because if we integrate, these terms already cancel. This They're simply the same. And to cancel other terms, we need to integrate it by parts. Just once. So it will contain boundary terms. So minus f times p g prime plus f prime p g from the second factor from x1 to x2. And the integral. So this vanishes. So finally, we have an equality that f prime, and also this term vanishes because no, we are studying zeros of g, so this term vanishes because g vanishes on the two boundaries. So this goes to 0. So f of x, p of so f of x1, p of x1, g prime of x1 minus f of x2, p of x2, g prime of x2 equals to the integral from x1 to x2 dx fg lambda 2 w2 minus lambda 1 w1. So now, is it fine? So we're exploiting the same phenomenon that if we study something Wronskian alike, then its derivative in x gives the difference of equations satisfied by each function. So the fact that this integral computes to this means simply that this integral originally was just a product, just a derivative of Wronskian. So, and if you consider Wronskian of solutions of different equations, then it is not constant as before. Like, because when I took two solutions of the same equation with the same eigenvalue, then this simply vanishes, and it tells us that Wronskian on the upper and on the lower limit is the same. But here it tells the change of this Wronskian. So we have this identity. Is it okay? Yeah. And now suppose that f does not have zeros in this interval. So in this case, we can choose both f and g greater than 0 in this interval. Mm. So the picture for g should be like this. G x1, x2. And there will be some picture for f. X1, x2, f. So if we do this, then right hand side will be positive. So this integral from x1 to x2 dx fg. So this is positive. But it equals to the left hand side. And wait, did I miss some sign? Probably. No. No, it seems that I missed some sign in this computations. Yeah. So, wait, actually, I missed the sign of equality. So it should be mm, so. Mm, if we want zeros of f to be between zeros of g, then uh, uh, f should have a bigger energy. So yes, I missed this Yes, I missed this equality or missed the two functions. Sorry, this should be this one. So this first function was our this function was g, and this function is f. So this is f. F has bigger energy. Sorry. Yeah, so the right hand side will be a negative then. On the right hand side is a negative, and the left hand side is positive, because f is positive, so f of x1, x1, p of x1, g prime of x1 is positive, because open this picture. Derivative of g is positive, f is positive. And on the other side, derivative of g is negative, f is positive. So minus something that is negative. And this is negative. And overall expression is positive. Where? In the first or in the second term? Oh, it is this picture. So g and f are positive functions. G has zeros x1 and x2, two consecutive zeros. So it is a contradiction. Oh, sorry, it is less than zero.
Cioè se f è positiva, la testa è negativa. Tu c'hai p che di nuovo decimale da questa è positiva, g primo di x1 è positiva perché è derivata da questa, e stessa g primo di x, p di x lo supponi positivo proprio per come l'abbiamo preso all'inizio, è proprio la p di x.
So
No, sono tutte e due, cioè quella a sinistra è positiva, quella a destra è negativa, quindi meno quella a destra è positiva, quindi tutto è positivo. Non faccio due cose positive, sono due cose positive.
is it fine? Mm-hmm. Yeah. So the correct picture is then the following. There's x1, x2, x2, and f crosses this interval somewhere. Probably there can be several zeros. It is not limited. Can be something like this, for example. So this is the correct picture. And this is a wrong picture. Right? Yeah. So now let's use this theorem to study something. So, for example, we can apply it to well, we can apply it to estimate the number of zeros of a solution of this equation for some, for example, big value of lambda. Namely, so this is the time to put p equals to 1 for simplicity, because otherwise I think we will need to write some integral functions for this comparison. So it's easier to do like this. So we have this equation. Let us put p equals to 1. So we have this equation: minus d minus f 2 primes equal to minus q times f plus lambda wf. And let us say that there is some so lambda is big, and there is some minimum of this function. So let us call it c equals to a minimum of minus q plus lambda w. And let us consider another equation, minus g prime equals to cg. Yes. Yeah, like this. Or we simply bound this function from below. And if lambda is sufficiently big, we are studying it for big lambdas. If lambda is sufficiently big, then it is positive. So we can write some equation with a positive c in the right hand side. Right? Well, this equation falls into our conditions. So
lambda is fixed.
yes, at the moment it is fixed, but we choose it to be some relatively big number, so that this c is positive. So it's some estimate for. By the way, it's not. Oh, how to say it? We can, in principle, study this for some smaller intervals, in a sense, we can study this we can choose some subinterval and the only condition for this subinterval will be that this function g has some zeros on this subinterval. But for simplicity, let us simply say that lambda is big enough so that this constant on the whole interval is positive, and we are studying another equation on the same interval from a to b. So from quantum mechanical point of view, it is kind of saying that there is some problem with big potential with big energy, and we are comparing it with some very simple problem with smaller energy. So is it clear that these two equations satisfy conditions of this theorem? So here we simply move q to the right hand side and say that lambda times w minus q is a single object. And this is all. This is another single object. Right? Yeah. So okay, right. So now let us draw a solution of this equation. So g is simply sine of. Let us choose g in this form. Sine of square root of c x minus a. So we will have some sine. That's a, and there is b somewhere. And so it divides this integral from a to b into some subintervals, and we know that each such subinterval contains 0 of the function f. So at least 1 0 of f. Maybe more.
The G must respect to the boundary condition, or
Hmm?
the G has to respect the boundary condition.
No, at the moment we are simply studying this equation as an abstract equation. We are studying the properties of this of its solutions as functions of lambda, and we need this to see how to satisfy the boundary conditions, because uh, mm, a boundary condition is that this zero should lie. So 1 0 should be in the point A, and another 0 should be at the point B. So so uh, now let us mm, we can also well, a number of zeros of this function is mm, number of zeros is mm, something like b minus a divided by no, maybe well, let us study this. So square root of c times x minus a equals to pi n. So when n equals to 0, yes, so maximum possible x is b, so square root of c times b minus a is pi n, where it must 0. So here it will be square root of c b minus a over pi. And so actually, if we want to find some estimate for the number of zeros of the solution, we should consider two functions. One for lower boundary, the function which is less than this, and another for upper boundary. So if Q does not have singularities, there is even no questions because we can simply find maximum of this function, and we will have another boundary with another c. So this tells us that a number of zeros in a number of zeros of solution is proportional to square root of lambda for big lambdas. So this is proportional to square root of lambda. And as we will see later, the number of zeros is the number of eigenfunction. So we can say that n is proportional to a square root of lambda. So in other words, lambda n is proportional to n squared. So it is some general estimate which comes from comparison with this simple equation with signs. And
square root of c times b minus a over pi is proportional to square of lambda.
Because c is proportional to square of lambda when lambda goes to infinity. Because when lambda goes to infinity, then this function w is positive everywhere. So when lambda goes to infinity, this becomes a dominant term. So when lambda goes to infinity, C will be proportional to a lambda a minimum W.
Exactly like superior part, integer part of that number.
No, there are no precise equalities here because this theorem says that we have at least yeah, at least 1 0 in each interval.
Yes.
So just estimate because it is and it is a very rough estimate because we are comparing this with solutions of absolutely different equations. So it's simply statement that if we have a equation of the form minus g to prime equals to some function times g, then if this function is bigger, is strictly bigger on some interval, then in some this function is strictly bigger, then solution of this equation oscillates faster.
I'm saying that the zeros of g should be maybe the upper integer part.
So if you want to compute the number of zeros of g, in essence, to write precise formula, then maybe yes, something like this. Yeah, in a sense that if c goes to 0, we have 1 0 at 0. No, like this, right? But it is plus minus 1, so it is not essential. No, but let us now think about solutions of this equation. Let us think about the eigenfunctions. So we want to study the following solution. Phi, so phi of lambda and x, phi to prime in x, minus between the x prime, equals to minus q phi of lambda x plus lambda w phi of lambda x. And this phi is defined by a condition that phi prime, so d in dx phi of So first, phi of lambda and a equals to 0, and d and dx phi of lambda and a, d and dx for x equals to a is equal to 1. So it is some solution of this form. So approximate form of it is this. So here is b, here is a. So it is some function. Oh, sorry. Some function which has some value at b. It has a lot of zeros, and and it can be either 0 or non-zero at this right point. So, and if you want a function from a spectrum of this operator, if you want it to be an eigenfunction, we ask it to be 0. Phi of lambda b equals to 0, conditions on a spectrum. And now let us see what happens with zeros of this function. So suppose that we find some eigenfunction. So we have let us draw a plot for phi of lambda phi of lambda n x. It will be some function which vanishes at this point. And now let us draw two pictures for lambda greater than lambda n and lambda less than lambda n. So here there are zeros of this phi. So there are two options. Lambda greater than lambda n and lambda less than lambda n. So phi of lambda x, phi of lambda x. So let us draw these zeros which we had originally. So this point is A and this point is B. A, B. A, B. And 1, 2, 3, 4. Maybe it's not enough space. So there are zeros of phi of lambda n. So what happens if we increase lambda? So zeros of a new function should be in between zeros of original function, because we increase energy, it oscillates faster. So this follows from the theorem we proved. So zeros of this new function are here. So all of them move to the left. It's the only option which is allowed by this theorem. So this function is like this. So it has one more zero in this interval from A to B. So zero from boundary moves inside. And if we consider this situation, when lambda is less than lambda n, then the picture is again it's too small b. And then the picture is like this: zero is here, zero. No, so it should be vice versa. So these zeros move to the left, and these zeros should move to the right, so that zeros of old function lie between zeros of a new function, like this. So here it will be a picture like this. So here we have 1, 2, 3, 4, 5 zeros, and here we will have 1, 2, 3, 1, 2, 3, 4, but it does not vanish on that boundary anymore.
Okay, so lambda is an eigenvalue. I don't understand. Lambda is an eigenvalue.
Yes, because for lambda n, this function vanishes at the right point. Now we study what happens if we consider a higher lambda and a lower lambda. So we have this picture that if we increase lambda from lambda n, then we increase the number of zeros, and when we decrease it, we decrease a number of zeros.
Why an eigenvalue must satisfy the condition?
Because well, it is just some particular case of boundary conditions. So I propose to study the problem with zero boundary conditions. And it's the most common problem. Maybe it will be just more complicated if we study the arbitrary problem. So, uh, so it's for simplicity. So it's not a big deal to solve the differential equation itself. In a sense, we can always satisfy one condition simply choosing correct solution in the two-dimensional space of solutions, and this can be fixed by scaling. So this solution exists for any lambda. But if you want it to be the eigenfunction with correct boundary conditions, we need to solve an equation for lambda, as we did for sines, for example, as we did for Legendre polynomials. We adjusted lambdas such that one function vanishes, another function is regular at the end of the interval. So, so so there is this condition, and we see what happens with this condition. So, so we see that increasing and decreasing lambda makes these zeros move, and some zeros can disappear at the end of intervals, or can appear depending on the change of lambda. And we also know this estimates, very rough estimates obtained from comparison with sine function. So we know that if we consider some big lambdas, then we can have arbitrarily many zeros. So it means that this process is infinite. In a sense, we have infinitely many solutions. So first we see that if we decrease lambda, then we can finally go to we can finally come to solution that does not have zeros, and it will correspond to lambda one. Uh, and if we go in the opposite direction, we will have a solution with arbitrary number of zeros, and they will correspond to all these lambda n's. So it is so because if you have a solution with some number of zeros equal to n, and if you have another solution for another lambda with some huge number of zeros, then these zeros should somehow appear when we increase lambda, and the only way for them to appear is to emerge at the right side of the interval, one by one. So the picture essentially is essentially the same as for sine functions. The only difference is that now these functions are not sines. There are some complicated function solutions to this ODE, but general property is the same, and the asymptotics of energy is also the same. So, are there any questions about this?
Just the picture, I mean, so, okay, because you, to prove that the number of zeros, uh, because we want to prove that the number of zeros of
Actually, it depends on boundary conditions. If there are boundary conditions with f prime equals to 0 at the boundaries, or if there are this if there are this polynomial boundary conditions, then a first solution will have no zeros, so it can be shifted by one. Yes.
we want to prove that the number of zeros of what function?
Of the eigenfunction. So
Okay, we want to prove the number of zeros of the eigenfunction is equal to the number of the eigenfunction.
yes. So we see, so using this theorem, we easily show that position of each particular zero is a monotonous function of the energy. So if increase of the eigenvalue of lambda, if you increase lambda, then all these zeros move to the left. If you decrease it, all of them move to the right. And
that's clear. That's pretty clear.
Mhm.
I mean, okay, the like the solution of that equation are the eigenvalue of what we are studying.
So
The solution of the equation up there.
So they become eigenvalues only if this is satisfied.
Okay. Okay. Uh, so um, for example, okay, in this case, okay, if we pick okay, lambda that satisfies that condition over there. Okay, we start to increase lambda. And to a certain point, we achieve another lambda that, okay, that has zero in B.
Yes.
Okay. At this point, uh, we have found two eigenfunctions.
Yeah, so we have this picture, another picture with 5 zeros now. B, mm, something like this.
Exactly. Okay, but this
I
point
know
we
it's
found
not
two
5.
eigenfunctions that have a different number of zeros.
With different lambdas. Yes.
But you're saying that the number of zeros of an eigenfunction is equal to the number of the eigenfunction.
Yes. So, well, maybe minus 1, maybe something like this. So the first eigenfunction has zeros only on the boundary. So, number of eigenfunction is 1 plus number of zeros is a number of the eigenfunction.
But you mean number,
Like,
like the position.
like lambda first, lambda second, lambda third, and so on.
Okay.
Positional number.
You mean like, okay, if a function has n zeros, that is the nth eigenfunction.
Yes.
Okay.
So how is it called? How to call it correctly? Positional number, order? No. Mm,
Okay. Okay. This proves also that yes, this proves also that the set of eigenfunction is discrete.
yes, because they simply correspond to solutions of this equation, uh, and we see how solutions of this equation look like. So we even know the asymptotics of these solutions. So we know this, that lambda is proportional to n squared for big n's.
No, la intende che cioè, il numero di zeri di una eigenfunction è uguale, cioè più 1, no, è uguale alla posizione dell'eigenfunction. Cioè tipo se una eigenfunction ha n zeri, quella n, cioè n più n zeri, quella è n più un'esima eigenfunction. But also okay, to see that it is discrete, maybe we should argue that the zeros of these functions cannot be captured. A solution of that equation cannot have accumulation. The zeros of that a solution of that equation cannot be an accumulation point. Like I cannot have
Yes, but we simply see what happens when we study this. We study the eigenfunction around its zero. If we so nearest zero in the x space, so nearest zero of phi in x is separated by some distance because we know this theorem. We can compare it with some assigned function, so it cannot have infinitely many zeros in some interval because because if you take some function with bigger energy, its zeros should fit between zeros of our function that we study. So nearest zeros are separated by some distance, and and when we start varying lambda, then this function immediately becomes non-zero and is non-zero for some in some interval in lambda until the next or the previous zero comes to point B.
Breaks the continuity of the next function to study, I think.
Yes.
If the zeros are too arbitrarily too near to each other, okay, the next function must have zero there, but then cannot be continued.
Uh, well, maybe it's not about the continuity, because yeah, maybe we can also think about the continuity, of course. But here we can simply find the distance to nearest zero using this argument about positions of zero of functions with different energies. So just so is it fine? Mm, mm. Okay, so sorry for delaying. Thanks for your attention. So next week you're coming, right? Because it's kind of the last week before Christmas.
I will not be there next week.
Ah,